Thank you for inviting me to speak with you this morning. My subject, as you know, is to summarize in a very short time the cutting-edge research, if you will, that was presented at this world meeting that I attended. It was actually the largest meeting of MS researchers that has ever occurred. It was a meeting that involved investigators from Europe, America, and South America, as well as Canada. So, if I can have the first slide, please. Now, this is extremely abbreviated and skewed. I presented a similar talk yesterday in the morning to health professionals. So this is, again, an abridged version of what I talked about. But I don't see my slide. So I can talk about my family, the grandkids. I can do that they're very cute, as you know, as they have to be, of course, by definition. They're all wonderful. All above average, of course. Now, I've been caring for MS patients, as you heard, for a long time. And ever since I started, people have asked me, well, you know, when is there going to be a cure? And when I first began, when I was just out of my residency, oh, what happened? Who's shutting down my computer here? Okay, well, we're going to cancel that. Everything was in the mouse. Yeah, you can see the mouse. Well, there we go. All right. Okay. Anyway, ever since I've been caring for people with MS, I've been asked the question, most appropriately, when is there going to be a cure? And of course, when I first began, I said, oh, about 10 years. And then 10 years later, I said, well, in about another 10 years. And so this has been an ongoing effort, of course, by thousands of individuals. And what's happened over the years, which I think is very exciting, actually, even though to an extent it's been frustrating, is the fact that as we learn more about MS, the more complex it gets and the more questions that are raised by the research findings that we have. So I can just say a few words about myelin repair. Everyone wants to stop the disease process, of course, but what about the repair of lesions that have already occurred? It turns out that there is a reasonable amount of myelin fixing or remyelination that occurs in the central nervous system. It's not normal myelin. It's myelin that is thinner than it should be. And on MRI scan, when you see a lesion or a spot or an abnormality, you can't tell whether that's a new lesion or a scar or one that's healed. So it becomes very, very difficult to really understand what's happening in terms of any remyelination that's occurring. But it turns out that there were some recent data presented that showed that there are two populations of people with MS, those that have the capacity to repair areas of demyelination and those that don't, so that it's almost as if there were a genetic predisposition, if you will, for the ability to fix areas that have been demyelinated. And of course, this raises very important questions. What are the genes involved that perhaps might be affected? What kinds of MS do they have? Do they have a milder form of the disease if they remyelinate, or is the remyelination really not a factor in terms of allowing a person to recover? And why does remyelination fail? Why isn't the central nervous system able to regenerate itself and fix itself? And these are all very important questions. There are two possibilities, as you can see here. I don't know if my laser printer shows up. I guess it does not. But you can have two possible conditions for a failure of repair. One is you don't have the cells there that are able to fix the areas that have been destroyed. These are called oligodendrocytes. These are the cells that make the myelin. Or you can have the cells there, but they're inhibited from doing what they're supposed to do. And that's, of course, to remyelinate. So it turns out, quite interestingly, and these are very new observations, really, that oligodendrocyte precursors, the cells that are there and can regenerate, are there in adequate numbers. So it's not a failure of lack of potential, it's that there are inhibitors of these particular cells that are keeping them from doing what they're supposed to be doing. Why does that happen? Well, I don't know the answer, obviously, but I can hypothesize anyway that you want to have a brain that's fairly stable. You don't want to have nerve cells growing where they're not supposed to be growing. You want to have a stability. So there are inhibitors normally occurring in the brain that keep variation from occurring within your central nervous system. But these may be very, very important in terms of allowing the brain to heal, and some of them that were discussed at this annual meeting are shown to you here. I'll talk about two of them. The first is a gene called Notch. Now that was described in the fruit fly. And animals that had abnormalities of this gene had notches in their wings, which is why they were called Notch. But this is a very important gene that we all have, and it's involved in making us segmentally oriented. In other words, putting our arm where our arm should be, our legs where our legs should be, keeping an arm from coming out of our chest. So these are genes that are involved in orienting a body as it develops. And it turns out that they inhibit oligodendrocytes from producing myelin. The second one is called LINGO-1. That's another natural, normal inhibitor of remyelination. And so what happens when you inhibit the inhibitor? What happens if you keep these particular inhibitors from acting? And this is shown to you here. As you can see, this is in the mouse. This is all animal work now. So really none of this has been done in people. But I think it offers us a precedent, if you will, or at least the possibility of this being done in people with MS. And what you see here is a spinal cord from two animals that have been exposed to various myelin proteins, and as a result have an MS-like disease called EAE, experimental autoimmune encephalomyelitis. So they have an MS-like disease, and the top spinal cord, as you see over there, is one that has lost a lot of myelin. The myelin is actually these little round circles that you see at the top. And you can see underneath them that there's been a loss of myelin in the spinal cord. And if you inject animals with this MS-like disease with this enzyme, it inhibits Notch. And as a result of that, you have, in the untreated animal, a loss of nerves and fibers. But if you inject this particular enzyme, what you see here is remyelination. So you've enhanced the ability of the central nervous system to heal itself by inhibiting this particular gene. Very exciting, because this really offers us our first opportunity to try to have a similar situation occur in people with MS. What's important, of course, is not only that you have remyelination, but does it result in functional improvement? Do you get better as a result of that? And these are observations that I think will have to be made in the future.